Hey everyone, this video is on quantum mechanics and more importantly on deriving Schrodinger equation. This equation is the most important equation in quantum mechanics which describe the nature of particles and also the nature of waves and how it works. So we derive the Schrodinger equation, and to show what is this is the Schrodinger equation. This is what we called as Schrodinger equation. This is the Schrodinger equation. This is iota, reduced Planck constant, derivative of wave function. This is wave function is equals to minus reduced Planck constant square upon with 2 m mass. This is gradient. What is gradient? To tell it is this. Differentiation, partial differentiation of anything in 3D, in 3 dimensions. This is what we call as gradient. So we start now what we known as the Schrodinger equation. So first we have in classical mechanics, energy is equals half mass times velocity square. This is the most simple equation of kinetic energy, and it is also the foundation of Schrodinger equation. So by simply call the manipulation, we get mv dot mv upon 2m. This is also the same formula, and by this we can call momentum dot momentum 2m e. They all are the same things. And to derive this Schrodinger equation, we have this is the whole thing, but for the main purpose we have to know what is wave function. We have to use wave function. So let's fit the wave function in it. We fit the wave function, but it is still not this. We have to know what and how this will come. So we have to get this by some operators. The operators are simple. They are simple operators for quantum mechanics, which we call the energy operator and momentum operator. These two are operators which we still don't know, which we derive in this video. So if we put them these values, we find the Schrodinger equation. So let's start with energy operator. So by considering a free particle moving in one dimension, we have a wave function which is like this: amplitude, wave number, x minus omega t. This is a free particle moving in one dimension wave function. So using Planck-Einstein relation, we know that A is equals reduced Planck constant omega, and omega is equal E upon reduced Planck constant. This is what we know. And we also know the de Broglie relation, which is P reduced Planck constant K, and K is equals P upon reduced Planck constant. So by putting these two values in this equation, we get a wave function like this. this, and by taking commons of reduced Planck constant we get this. This is also wave function, but not purely a wave function. If we do this, nothing will happen. So we have to differentiate wave function with respect to time. So differentiating the wave function with respect to time, we get this. This is the partial derivative. And here is that. This is the differentiation, partial differentiation of wave function with respect to time, and using the chain rule of calculus we get this. Using the chain rule we don't get this, we get this. I'm writing the same thing after all. This will become, and we have this thing. So by this we have this, and this is as we all know, the wave function. They both are same things. So this differentiation of partial differentiation of wave function minus IE reduced Planck constant wave function. Now we are more closer to what is energy momentum operator. Energy momentum. Why energy momentum? It's only energy operator. So multiplying both sides by reduced Planck constant upon minus I, we get E wave function is equals reduced Planck constant minus I, and this term will cancel out and this will remain. So since we know that 1 upon minus I is I, so energy wave function will become this and this, and removing the wave functions we get the energy operator, which is iota reduced Planck constant partial derivative. This is the energy operator. So let's find out what is this momentum operator. So doing the same thing with that same equation we have written down, using the same relations and same everything, we get this. It is a straightforward, a simple relations. So differentiating wave function with respect to position, we get the partial differentiation of this and using chain rule we bring down the coefficient x in the exponent, which is IP upon reduced Planck constant. So by this we get partial x, and this will not this will become this, and this is, we get e a e I upon reduced by constant px minus e t, and we know this is the wave function. We get to this, and we have to do the same thing, but this time we have to divide both sides by reduced Planck constant upon I. I sometimes think why this, but it is the way it has to be. So we get reduced Planck constant I, wave function, and this. We get this term we cancel out by this, and we remain with this. So as we all know, as always, 1 upon I is equals to minus I. So putting this, we get minus I h wave function in the x direction, and removing the wave function and doing this in all 3 dimensions, we get momentum operator minus I reduced Planck constant gradient. This is the momentum operator, and putting all the operators in that equation we made, putting this value in this equation, we get what? The Schrodinger equation. This is the Schrodinger equation. We get it. It's the Laplacian, and here is also a wave function which I forgot to write. So where does this minus I goes? To tell this with I square is 1, simply 1. This has to be and this equation tells us about the whole mechanism of the wave functions. That is the whole story you have to do. This is the minus 1, and this minus will get positive. This value will come. So now, what is the drawback of this equations? It didn't produce the right prediction what we have to get. It predicts something odd and not very peculiar about our mechanism of macroscopic world. Like, it predicts gold as not a gold color, it predicts gold as a silver color, but that's not correct, as we all know. So we need to get a better equation, and also it has some drawbacks, that this is Laplacian. What is Laplacian? This is Laplacian, double differentiation in all the dimensions, and this is the single differentiation, so it won't correspond, and it's not not an elegant way to describe the equation, which is not on the basis, on the very fundamental basis, not differentiate on the same numbers. This is a square and this is not a square, so we need equation which also solve this. So by this we get an equation which was made by a scientist named Paul Dirac, and this equation is very good for everyone, which is this. this is what we call Polynomial equation. Here we get the solution of this thing, and this wave functions also produce something, a prediction of antimatter, because this wave functions produce positive upspin, positive downspin, negative upspin, and negative downspin. So energy with positive is, as we know, that E is equals mc square, but we don't know that it also has to be in like E plus minus mc square. We get this by this equation, and the person who resolved this thing by making some diagrams is Feynman. Which book is this? The Richard Feynman. He solved the thing by some diagrams, which we call as Feynman diagrams. And here we get the solution, and we get what real quantum mechanics has to be. And now in CERN, the anti-atoms were made. So this whole thing about quantum mechanics is so much great that we didn't even know how does that be, but it has to be like this. So thank you for this, and I will do more videos on quantum mechanics by deriving this equation. We derive this Schrodinger equation. We will derive also this equation, and also Clark-Gordon-Fock equation, which is also the relation between Einstein equation and the Schrodinger equation. So we will derive this and also this. This is the modification of Clark-Gordon-Fock equation and this equation. And after that, we will go into special relativity, general relativity, and to write the black hole solutions, Schwarzschild equation, Kerr equation, and many more equations and solutions, and to write the Einstein field equation. And after that, we will go into a more rigorous things like quantum field theory, which very hard a subject to tell. And also we go into the string theory, quantum electrodynamics, quantum chromodynamics, and quantum electrodynamics is more about Feynman to tell. And after all of this, we go into my own theory on the theory of everything, and more to say universal expansion theory. What is that? What is that universal expansion theory? We don't know what are this. So this is the equation of mine. I made this. That is the equation I made, and this is K. But wait, this equation looks like Friedman equation. Yeah, it looks like Friedman equation, except this value. This is the expansion factor, which produce a little more a reason how does this happen. This is the mechanism, and this is the reason why does this happen. This beta and rho to power n. So we will derive this and also derive the black hole solutions and resolving the singularity and many more things in this series after a long time. So thank you for that.